All right, this is Wednesday, November 4th, day after the election. I'll go ahead and share the screen. Hi, everyone. Unless somebody has something to say, I'll share the screen. I guess you could say something even if I'm sharing the screen. Okay. Yeah, I was talking to the students today about this sessions, and I told any of them can come by too. But I like it. I like the one we did yesterday when I finally got you guys to say some stuff because it really helps. It helps the viewer when you guys are asking questions. I don't want to just go on and on and on, but if something doesn't make sense to you, I mean, you're all bright people. So if it doesn't make sense to you, then it didn't make sense to them. And they tend to sit and say nothing. So you have to have agency, and I gave him a big speech about this. That you have to have, if you don't get something, it's up to you to say something. So I feel like you all have agency. You all are going to ask if you have questions because this is the only avenue you got. So it'll help them if you guys have a question. All right, we've already had this announcement. This hadn't changed. And then I just added these Zoom wrap up times every day. And just remember, we're not doing it on Friday. I'm only doing it Monday through Thursday. And Friday, there won't be one, it won't be a live one, but I will do a wrap up at some point Saturday morning or Saturday at lunch or something. And it'll be up by Saturday early afternoon. We talked about this in here yesterday, number 2 on the homework. This is due tonight at midnight. You may have already turned it in, but this came up in class again today. And you do have, and the question came up in class, why do you have, why are there 3 boxes there when it's just V is equal to omega R? But in this case, it's a special case of that because omega is, when it's one complete revolution, that is 2 pi, and the T then is a special time, and it's called the period. And the symbol for the period is this TP, capital T. So a lot of times, like we talk about the radius of the Earth, if I'm just going to talk about radius, I would just say, in general, I'd just say R. But if it's a particular radius, like the radius of the Earth, then you capitalize it and put a subscript. All right. Little tidbit, little pro tip there for communicating, your communication skills in physics. Okay, so today we're going to work on number 5 because I told you I'd do that, and that 5 I would consider a hard. It finally we've worked some in the medium category, where we've worked some unit analysis in the easy category. I would say 5 is the first one we've worked in the hard category. Okay, so we'll do that, and then we're going to spend the rest of the time going back over this, rolling the ball down the ramp and how that changed everything. All right, so I'm going to come back, and we'll spend a lot of time diagnosing that graph, and it'll get us to what we call the trio, and it'll be the beginning of calculus. I mean, it's already kind of begun, but it's another step towards the calculus. Anyway, let's get this done first. So this one, maybe you've tried it at home already, but if not, let's knock it out. Okay. So it has an altitude of 156 miles. And I got the globe out in class, and I asked the kids, where do you think the ISS, and I use this little screw here. I said, if this were the ISS, where should I put it? And some kids say, well, it's way a ways away. But then we realized that it would be right above. The globe is like this big. It's right above the globe because it's only 156, say 160 miles. It has a slightly elliptical orbit, but above us. So if you got in your car and drove straight up and you're driving to the International Space Station, you'd be there if you go 75 miles an hour in about 2 hours. So it's not that far away. In fact, you can see it at night. I think a month ago, you could look out and see it over Oklahoma. It goes at it goes, it only takes it 90 minutes to go all around the world. So it's extremely fast. And that's here too, 90 minutes. So we have to, there's the two givens. And so we're supposed to put what the symbol is. Well, what is that? Hey, I'll ask you, what symbol goes with that 156 miles?
Wasn't it H, I think?
Right. Oh, we already did this. Did we already do this together?
No, we did something like this, or that's how I remember.
Well, that's a good memory. This is that it is H. H stands for height. Okay, the lowercase h. Now, uppercase H stands for enthalpy or hydrogen. So chemistry has those, but lowercase h stands for height. This is the RE we talked about, the radius of the Earth. And then this is the TP. That's the period of the ISS around the Earth. So it says, what's the speed in miles per hour? All right, so I'm going to end up over here ultimately in velocity. So I'm going to end up in miles per hour. Always got to know where you're going. So let's go ahead and do a quick. Now, the reason why I brought out the globe of the Earth was because I had students kind of draw it up. Well, students were drawing this. They're drawing an Earth, and then they put the ISS out there. And that's a no. It's that's a misconception. That may be, well, that's too close for the moon, but that's something further way, that's like a geostationary, way out there, geosynchronous orbit. So the ISS is in low Earth orbit, LEO, low Earth orbit, they call it. All right, so you would draw it, when you're drawing it, you want to be somewhat close. So on the drawing, I ended up making the Earth huge. The Earth is like, I'm going to do a quarter of it. So the Earth is like this. Okay. And then the ISS is like right there. So we do the radius of the Earth. If that's the center, that's the RE. And plus we have the height, H. All right. And then we're trying to find the velocity, trying to find the V. Trying to make this look nice. I'll probably take a picture of this one for the group. And so I'm trying to find the velocity, not V bar, just that's an arrow. That's all I know. Now you go, well, you can write down the numbers. Well, I already have I need the symbols and the good symbols in the drawing, and I'm happy. I probably need to put V equals question mark. Okay, now I know I got a graphic of what's going on. And that is the Earth. Fine. Okay. Now, I mean, I don't want, this is a video, and I don't want to, I mean, you guys are bored enough sitting there watching, but then somebody watching a video of this, so I want to move kind of fast, but I'll certainly answer your question. And so we have V equals R omega, but then we just like the last problem, omega we said was really 2 pi over TP being the period. So we put them both together. And these are just symbol thoughts, right? They're equations, but they're symbol thoughts. I'm not putting numbers in. I could put coefficients in. They go, well, yes, you did put a number in. You put a 2 in there, but that's a coefficient. Okay, I'm not putting in constants from the problem or anything. Isolated variable equation. So here I have the V. We're going to put them together, and V equals R omega, which is R. Wait a minute. Careful. R here on my symbol thoughts, R is actually RE plus H. It's a combination. So V equals RE plus H over, well, times 2 pi. Okay, fine. Times 2 pi over TP. Okay, Now I have for next year, as you can tell, this looks different than yours. I've enhanced it for next year. It's even better than this, but I see that box, that third box, I made it big because we're going to, in this problem, we're going to have to do a unit analysis inside a unit analysis. It's like those Barishka dolls, those nested Russian dolls. Sometimes in physics, there's an equation inside an equation. There's really problems where there's an equation inside an equation inside an equation. All right. And I call those equations, they're like suitcases. So sometimes you'll open up a suitcase, there's another equation inside it. All right. More about that later. But anyway, so here we go. We put a 2 pi there. I just combine the pi is kind of a coefficient essentially. So 2 pi, I do the 1 over TP there. And then this one's going to be the RE, the radius of the Earth, plus the height. Okay. So here we go. Come down with the numbers. Let me change my color radius. Well, right there, this one so far, if this thing's worth 40 points, you probably have 25 right now. You've already gathered 25 points. So let's go blue now. So I have 2 pi, 1 over TP. TP is 90 minutes, so 1 over 90 minutes. And then we have RE plus H. I've got, okay, this is where it's a unit analysis inside a unit analysis. Because the RE is in terms of kilometers and the H is in terms of miles. And I can't add miles. It's like adding apples and oranges. You can't do it. You know, you can't say, well, 5 cats plus 3 trees equals what? You know, so you have to actually put them into the same units. So a little miniature unit analysis. It's cute. In there, oh, okay. Miles, I want miles in my answer. So that's already okay. I'm going to leave that alone. So that's plus, it's at 156 miles. Now, the RE then is 6370 kilometers. I'll blow this up over 1. I got to get that in terms of miles. So, you know, kilometers down here, meters, 1,000 meters up here. Okay, from the units I gave you, meters into feet, so 0.305 meters under a foot, and then feet into miles, 5280 feet in a mile. Okay, so bring out the green kill pin just to make sure. Kill, 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 kill. Okay. And then this is all over 1. Just a 1 down there. All right, are we done? That's all the givens. Now if it's, sorry, it's about to lose juice. Okay, if this thing is worth 40 points, I've gotten 35 so far. What do I have left to do?
Convert minutes to hours.
Mm-hmm. So we'll convert the minutes into hours. We got 60 minutes, 1 hour, green kill pin, and minutes go away. Hours I'm keeping, miles I'm keeping, and everything else dies. Yay. And when you do the math, you get, I'll save you the time here. You get 17,000, I think 336 or something. We'll say to 3 siggies anyway. 17,300 to 3 sigs miles per hour. Now that's crazy fast, obviously. The fastest when I checked this a couple of years ago, the fastest land speed, and you can double check me on this, you can look it up on Wikipedia or something, but the fastest land speed There was a big contest. We did an article a few years ago. There's a big contest there was anyway, between the UK and the United States on who can break. They were trying to get to 1,000 miles an hour. And so let's just say that the fastest land speed, and that's like the blue flame, right, in the desert, is around 1,000 miles an hour. It's as fast as we can go on Earth. But this ISS, and showed a picture of it all. But if you don't know what the ISS looks like, you need to look it up. Okay, if you're going to go into physics, you got to know what the ISS. Big, it looks like a big, I don't know, it's big tin can up there, but it's got all kinds of, solar panels and all. Anyway, and then someone asked, well, are there humans on that? Well, yeah. I mean, there's Americans, there's Russians. We just hitched a ride. Our last ride we hitched with Russia at about $80 million it cost us. Ridiculous. There's Indians from India on there. There's, all kinds from Africa. There's people from all over up on the ISS. And because the reason the student asked that, they go, wait a minute, how can a person go at 17,000 miles an hour and live? And I thought that was a brilliant question, that's thinking. And it's true. It's crazy, right? But aren't we on Earth going at like 64,000 miles an hour right now, just sitting on Earth? So it's not, in physics, it's not the velocity that kills you, it's the acceleration. I don't feel velocity. I can be driving in my car at 90 miles an hour and sipping a cup of tea, right? Or playing ping pong on a cruise liner. You don't notice it. Only if you either turn. Now, if I'm driving 90 miles an hour and I turn to avoid a squirrel, I'm going to notice it now because inertia takes over, which we'll get to. Or on a jet, going 600 miles an hour, but you can have your coffee and eating your little peanuts and not notice it. It's only when that jet takes off or lands, or you hit turbulence, that you accelerate, and that's what the body feels. So the body does not feel velocity. Okay. So at 70,500 miles an hour, you're not going to feel that. But think how fast that is. Now, someone can check me on this. I know in meters per second, the speed of sound is 331, Mach 1. And we had this, I'm not just riffing here, we had this discussion in class. Mach 1 is 331 meters per second. I think that's about 740 miles an hour, somewhere in there. So let's say it's around 750 miles an hour or so. Well, that means I can divide that into that, 20 times or so. So the ISS is moving at Mach 20. That's a conservative estimate. Mach 20. The fastest plane is like the SR-71 or so. It goes about Mach 3. Up in the upper atmosphere where there's not much atmosphere, you could not go Mach 3 if you're only a mile up. You got to be way up there. Anyway, so this is going to Mach 20 because there's no atmosphere up there. I mean, there's a little bit of the atmosphere actually goes out 500 miles, but they're 156 miles up there. Atmosphere is like a soup, and we're down here in the mucky muck. It's really thick. It doesn't seem like it is, but all around me, this is thick soup. If I go up, if you go to Denver, I mean, it's much thinner air up there. If you go to the Colorado Rockies, when you go skiing, right, you can't breathe as well because the oxygen, there's not much oxygen. If you go to Mount Everest, you got to wear oxygen because it's 5 miles up. And so the further up you go, the less air particles there are. And so up at this 156 miles, there are still air particles. If you're in the exosphere, I think, up there. You're way beyond the troposphere and the stratosphere and the mesosphere. You're up like in the exosphere, but you're still in our atmosphere. Okay. But the thing is, there's no air drag up there. Remember, air drag, we did this one before. RA is 1/2 d rho a v squared. There is no, this rho the rho there stands for the density of the air you're traveling through. So if I throw a baseball, it's got, or a volleyball or something, it's got a lot of air that cannot get out of the way fast enough, and it slows it down. But with the ISS, yes, there are still some oxygen up there. Believe it or not, there is some nitrogen up there, but the particles are really low density. Someone can look it up, but the density, I'm sure there's a table that shows density of air as you go a column above your head. I have it in I visualize that because I know I have that somewhere, but I don't remember exactly what it is, 156 miles. But it's really low. I mean, on Earth, the density is 0.0012 grams per cc per cubic centimeter. So it's even small here on the surface. But when you go up there, it's 0.000000, 1 gram per cc. So the ISS can go at Mach 20. Now, someone said, well, how fast is that? I mean, relatively speaking, well, a bullet out of a gun, a typical bullet will travel at Mach 2 or Mach 3. When the bullet first comes out, let's be conservative. I'll throw a 22 here, a 38 maybe, comes out at Mach 2. But we're doing 10 times. And this is ballpark, 1 sig fig. Back, a physicist call these discussions back of the envelope. I'm waving my hands a lot. That means it's back of the envelope. But so, that's how you do, how you think through things as an engineer. You go, well, with how much water can this dam hold, But so the ISS is moving at Mach 20, which is 10 times the speed of a bullet. That should give you pause. If I'm in the ISS, I'm moving at 10 times the speed of a bullet. There's the key, and I'll post it, but I may post the colorful version too. Okay, so that's not what we're here to talk about. That's warm-up stuff. And a student said in second hour, said, "Man, this is a hard day," and it is. I mean, I was talking to Rose before we got started, and I didn't go to sleep till 2:30. Got up at 7:30, so I don't know, 5 hours. Big election and all. So we talked, yes, I'm a little bit worn out. I'm sure you are too. We talked about about Galileo by dropping balls and trying to time with his heartbeat. It just wasn't going to make it right. So he diluted gravity by having the ball roll down an inclined plane. And if the inclined plane's only 5 cubits, 8 or 9 feet, Galileo's not going to get enough heartbeats. So he kept improving and making them longer. And Salviati was the guy that worked for him. He was Salviati was sort of his right-hand man. And so he gave Salviati these instructions, and Salviati was like scratching his head. So, what do you want, boss? 35 feet? I mean, which is like, cubits, 20 cubits. But he wanted it really long and straight because he's trying to understand the Earth's gravity itself, which think of how, what a heady thing, how much confidence that takes. Egocentrism, I guess, or maybe narcissism. I don't know if Galileo was a narcissist, but just to think that you could, that you were going to be the one who figured out why things fall to the ground and what gravity is. The nerve of this guy. But it takes that kind of people to move us forward. So anyway, because he was sick and tired of these idiots that surrounded him talking about flat Earth. Like, those people aren't around anymore, are they? I mean, but people talking about that gravity is mystical, and that's what happens. People don't understand something, so what do? They call it magic, or they ascribe it to God, right? That's what we've always done through history. And what physics does and science in general is it takes those notions and actually explains them. And people don't like that. People don't like you explaining how things work. They would rather say God did it. So Galileo is dealing with this directly with the church. But the church is okay. They don't know what the hell he's doing. Galileo, you're down there, you're playing with this ball going down a ramp. Who cares? But anyway, so what he concluded, and we showed this. This is where we ended up kind of yesterday. He concluded that, and this is phenomenal, but he concluded that position when a ball rolls down a ramp due to gravity, its position changes with the square of time. This was such a paradigm shift that it was ignored. That's what happens when you do a paradigm shift. People either mock you or they either mock you on Twitter or they ignore you, right? I think I'd rather be mocked, but they ignore you. So this idea here was ignored until, as today we're going to talk about, until somebody else took up the mantle, and that had to be the next genius, which was Isaac Newton. The year Galileo died, Isaac Newton was born. And I read an author one time, a historian said, well, the world can only handle one genius at a time. Now we have Donald Trump, so I don't I don't know who we're going to get after he goes. Okay, sorry. Gotta watch myself. We're in Oklahoma. All right, so nature paints with a broad brush. Okay. So what I want to do is, this is a smooth curve, and I didn't do this in class, but I want to do it with you guys. You're my last hope. Let's blow this up. Once you have drawn a smooth curve, you should wipe out and erase your dots. Ignore from now on. So they can go through and erase your dots. They're just going to get in your way. We don't want those dots. They've served their purpose. Now kill them. Okay, I'm going to go through and I'm tidying up my, you want to make sure that your curve, it looks good. There we go. I'll leave that guy. That's the first. I'll leave him there. Let me get this guy. You really should ask ask who's ever got the money in the family. Ask them for a iPad for Christmas, because I have students that use iPads, and they kind of do their notes on iPads and stuff. It's just easier. You can organize your stuff. I think when I'm doing this for real, when I'm retired, I'm gonna require. Well, no, I'm not going to require. That's elitist. But I'm going to strongly suggest iPads. Okay. Just because it's more colorful and it's more fun. All right, so here we go. Now we're going to jump ahead from Galileo, who left this because, remember, the Danes sent him. He had a lot of friends all over Europe, and some Danes sent him a box of lenses. I got to remember to bring those tomorrow. We'll talk about them more tomorrow. Concave, convex, triangular, hemispherical. Sent him all these lenses that you could put on things and make it get bigger. They were like an oddity. And they thought, Galileo, hey, what do you think about this? We didn't understand light. No one, who figured out light was Isaac Newton, and he was still a good 50 years away. So Galileo then left this, and I read a book once, and the guy was saying that if Galileo had not been sent, I was telling this yesterday, I'm not going to repeat myself, but he may have invented calculus, but I don't think that's true. Okay. So I forget where I said things. but I kind of remember you guys because this is a different situation. Anyway, so Galileo left this and went on to, to invent the telescope. And he got in trouble. We'll get that tomorrow or the next day. Okay, so Newton then takes up the mantle later on. And thing is, Newton had more technology than Galileo. Newton had a graph. He had, because Rene Descartes had invented the Cartesian coordinates. And so X and Y, Newton could put it on a grid. And you'd think, whoa, Galileo was a genius and he didn't graph it? Because nobody graphed anything, okay? I mean, give him a break. This is graphing through time. Yes, the Greeks, the Egyptians, the Babylonians, they built amazing structures, the Parthenon, the pyramids, but that is not looking at an object through time, right? It's looking at an object, it's spatially, even three-dimensional. Fantastic, but not through time. That's my point. That's why I say Galileo was the first real physicist, okay? Not Archimedes. Okay. So Isaac Newton, now we're talking 1680, 60, 70 years later, Isaac Newton comes along and revisits this idea. And he says, okay, Isaac's trying to understand the idea of change, of velocities, of accelerations, and the mechanics of motion. All right. So he wants to know, what is the slope? So I ask you all. Oh, Natalie's there. Hi, Natalie. Natalie has missed class. Good. So I'm glad she did this. She's doing the right thing. Natalie's from third hour, I think. So, anyway, so I asked the class, what is the slope? This is the same question that Newton asked himself. I want to keep asking you guys questions. I want to try and force you to think like the greatest thinkers of all time. Okay. Galileo and Newton were easily the top 10 thinkers of all time, maybe in the top 5. Newton certainly was. So I want you to question the same and to make your brain work the same way their brain worked. So what is the slope? If I give you a line, okay, if I give you this line right here, okay, and I say, what is the slope of that line? You say, well, it's rise over run, right? If we're just counting boxes, it's 2/3. Okay. But now I'm going to ask you a more interesting question. And the question is, what is the slope of that curve? Now, that should cause you pause. Anybody got a comment about that? What's the slope of that curve? I asked the hot seaters this question today. Let's put it this way. What if I were to force you to answer? Force you to answer saying something. What would you say is the slope of that curve?
Can you not just do rise over run?
Okay. Let's do it. Do rise over run. I don't know. Pick these. Let's pick the beginning and the ending point, right? I'll pick this. I'll pick this. I'll connect them up. Like I say, I'm not wasting time. That's what we did in class. I'm committed to not wasting your time. So we look at that and we go, it looks like it's rising 8 meters in about 8 seconds, right? So I would say the slope of this curve is 1. Well, the problem is that is the velocity, but that is V bar. And V bar is 1 meter per second. So if I forced you to give me the velocity of that little ball rolling down that ramp, then, and you said it was 1 meter a second, I'm going to say, okay, you're in the right ballpark. It's not 1,000 miles an hour. It's not 1,000 meters a second. It is in the range of 1 meter a second, but that's making the assumption that the ball doesn't pick up any speed. So although that puts us in the ballpark, that is incorrect. That's all you could do though, if I force you to give me something. Okay, so now we're thinking like Newton. This is Newton's conundrum. How do I get the slope of that curve? Now, ultimately, this led to the beginning of calculus. This is how calculus started, why calculus started. That class that you may not like. You ought to like it though. I loved calculus. So what Newton said was, okay, I have this cool grid. I can take make it bigger. I can make my paper bigger. Well, I'll make my thing bigger. So when you do this, you can now take it and let's say between 4 and 5 seconds. Okay, I can go and look at that ball rolling down that ramp. Now I'll go to the middle of the line and let me use blue. So I go to the middle of that line and I come over 1 second from 4 to 5. And then I go back up and I see, well, where will I hit that curve? If I come up from that point, where will I hit that curve? To the center of that curve. Right there. Now let me connect these up. Yeah. Okay. Boom. So I have, and now you need a colored pencil. Okay. We're going to do a little coloring. This is going to be part of my coloring book. My Nature Paints the Broad Brush. I'm going to teach little third graders and stuff and fifth graders. I'm going to sneak physics in there without them knowing it. We're going to be doing physics. And then when they get to physics, they'll go, oh, this all looks familiar. Okay, so if I look at this one, that is delta. I'm gonna make this look nice. This has got to be the polished version. Okay, apologize, but it's got to be done. So this is delta t. Delta t is 1 second. Delta x is, well, it's counted up. Delta x is equal to, I don't know, what do you think that is? This is where you can probably get a ruler out, or you can get a piece of paper and try and do it just perfectly, but it's, you know, close enough. Let's see how far this is. That right there, that's about 0.6 meters. And then I throw this in there, and that's about halfway up, so that's 0.5. So we add these two together. Delta x is 1.1 meters. Okay. So what's my slope? My slope is my velocity, right? So it's still an average. So V bar equals, I notice how I made it simple on myself. I made the base 1 second. So V bar is 1.1 meters per second. Okay. Wouldn't you agree that now we know if I scan back out, that is that pink is a curve. But if I keep coming in and in and in, that looks flat, straight, right? So if I lived in a little house, let's say I lived in a little house right here, little house. And I don't get out much. And so I look out my window and I think that I live on a straight line, right? And I hear these people talking about this curve that we live on. And I think, no, I'm looking out my window and I live on a straight line. So I formed my own Facebook group, the Straight Line Society, and we get a lot of hits and we sell t-shirts. But in reality, it really is a curve. It's the same thing with the earth. I mean, flat earth, right? I mean, I look outside, that certainly looks flat to me. But in reality, it's a globe, it's an oblique spheroid. But so you see what I'm saying? So we can use that though, because it on a small scale, that looks to be straight. And I can get away with calling it, for that between 4 and 5 seconds, I can say the speed of that ball was 1.1 meters per second. Get it? Yeah, so I can do it again. All right, let's go to the next one. Let's go between four, that's 4 and 5 seconds. Let's go between 5 and 6 seconds. The little fourth graders are going to love this game. Come up here. I'll do little seminars with them. I'll be like the Mr. Rogers of physics. Okay, so now I do it again. And that is, once again, I'm keeping it, I'm lazy, I guess you could say, but I don't want to divide by a number. I'm just going to keep that 1 second. So delta t here again is 1 second. And now let's look at my delta x. Now delta x is equal to, I don't know, what do you think? That's 1, obviously. 1 to there, plus, what do you think?
1.3.
1.3, I'm not going to argue with you. I'm going to argue with you a little bit. I think it's like 1.4. That's just me, though. I mean, halfway these are the kind of questions you ask yourself. Remember, we're thinking like Newton, right? So 1.5 is right here. So from my point of view, it looks like 1.4. So you can know 1.3 if you want. I'm putting 1.4. We can agree to disagree on that. All right, so 1.4 meters. Okay, and then we do our velocity. What does that mean, our velocity? Well, it's simply the rise over the run, delta x over delta t. So we have v bar equals to, now it equals 1.4 meters per second. So finally this year, we have something that's speeding up. Between 4 and 5 seconds, that ball was rolling at 1.1 meters a second. Then between the 5th and 6th second, the speed went up to 1.4 meters a second. Okay. Now, we got to color this in. Now, what I want you to do, I'm not going to keep you too much longer. What I want you to do is, my wife's on, and today's her birthday, so we gotta go do some stuff together. Go eat out or something. So what I want you to do, though, tonight or after I leave you, is to do this thing all the way, keep doing this all the way up the curve. And we call this a stegosaurus tail. And in my book, we'll call it that stegosaurus tail. Okay. We'll have a little stegosaurus there. So you can see as you go, you can start at 0, up, over, up, over, up, over, up every second. And then find the velocity, find your V bars. And you probably want to call this, V bar 4 to 5, V bar 5 to 6, V bar 6 to 7, Now, last thoughts here, and then I'll let you go. Isaac Newton is thinking this way, right? This is cumbersome and slow. And he knows it's not adequate. But what he's done is he's taken that, he once you finish this, we're about halfway done at the most. But once you finish this, then you can start to look at and consider velocity and how it changes with time. And then you can finally quantify acceleration. Okay. Now, Newton did this up to the point where he pretty much had to invent calculus or he couldn't go any further. And we'll get to that story after Thanksgiving, but this is laying the foundation for calculus. Okay? Now, leave that alone. Don't worry about, well, go ahead tonight. When we come back tomorrow, I'll have this done, the whole Stegosaurus tail. So if you want to catch up and be up with me, then get your Stegosaurus tail done. And also 2.5 is due at midnight. Okay. Any questions before we go?
I have a question on number 3 of 2.5.
Oh, before you ask that, if you haven't picked them up yet, your notebooks are on my front porch. If your notes in them, if you haven't picked those up yet, if you did it that way, just warning you. I'll take them out again when I go to bed. I'll bring them back in, but and I put them back out about 1 in the afternoon. So they're out there from 1 in the afternoon until about midnight. Okay, back to your question number 3.
Yeah, number 3.
Okay. Number 3. All right. What do you got? Yeah. Oh, go ahead. It's way back here somewhere. Yep. Uh-oh. Close your eyes. Hold on. Go ahead, number 3. What's your question?
I just need help how to put it together.
Okay. Hold on. Get out of there. Okay. I didn't want you to see it. Because I had somebody with this at lunch today. So just there. Okay. Do this. All right. Number 3. So it looks like it's the funky chicken here, and we're going, that's our speed. Yeah, that's our V. There is our time. And so it's just a red equation, right? So we have delta X equals VT. So pretty simple drawing. You're heading towards Dallas. Oh, no, you're not heading towards Dallas. How many feet will he move in 2 minutes? Okay, so we're trying to find delta X equals question mark feet. Our time is 2 minutes. And the velocity is whatever it is. Velocity is this. I don't write it all down. That's good. I'm happy with that for a drawing. And then your thoughts, well, it's just simply the red equation, delta X equals V times T. It's already isolated, so V times T. So V times T, right? Was that a problem or the rest okay or what?
Yeah, I'm good. Thanks.
Okay. Anybody else have a question on that one?
I had a question on number 2.
Okay, 2. Got it.
We got it set up and I thought I did it right, but I'm just like a little bit over the correct answer and I don't know
A little bit
how that
over?
happened.
Well, I wouldn't worry about it.
Well, I have 65 instead of 64.
Oh, that is quite a bit
Well,
over. Okay.
64,000. Yeah.
Something probably a little bit off there then. We got 2 pi here. We got 1 over, okay. Oh, okay. The TP, of course, is the 1 year. Let's just say a year. That's how long it takes us to go around the sun. And then R is 146 gigameters. Then I go through it. All right, so get rid of some stuff here. I want to end up in miles. Oh, it could be a conversion you did there. So for gigameters, I got a gigameter down here. I got 10 to the 9th meters. Okay, let's get that to miles. There's 0.305 meters in a foot. And you're saying, whoa, you didn't tell us that. Well, it's a homework assignment. And so on a test, though, I would give you these kind of conversions, at least the feet to meters thing. And then feet to miles, 5280 feet to a mile. And then okay, I'm going to green kill pin, see where we're at here. Feet, I'll circle the miles, I'm going to keep that. Meters, gigameters. And then I got to get years into hours. So no one knows how many years in an hour off the top of your head. So year to, I don't know, 52 weeks, I guess. And then do weeks to days to hours, right? And that should do it. We should get the same answer.
Yeah, I messed up. I didn't go to feet. I tried to convert and it didn't work out very well.
Got her. So keep going, but then that's, you can do the rest of that. Okay, that's probably similar to the one that'd be on the test. That test we have on the Thursday before Thanksgiving would be something probably along these lines. More like 1 and 2, not 3. It won't be like that. More like 1 and 2. It won't be like 4 or 5 yet. Maybe 4, but not 5 certainly. Either 1, 2, or 4. It'd be somewhere along those lines. But you'll see on the take-home test. So. Okay. I guess we'll call her good. Let me stop the sharing. All right. So thank you all for coming. You make it so much better when you guys are here. And we'll do it again tomorrow. Tomorrow's Thursday. Then we won't do it again until Monday. Okay. Okay. I'll see you guys. Bye-bye.